Okay, students, in this video, I'd like to take a quick look at what's called the electromagnetic spectrum. First of all, electromagnetic is abbreviated EM, electromagnetic, and the electromagnetic spectrum is a diagram or a chart that shows all of the different types of electromagnetic radiation. And now this radiation, when we use this word, we are not using that in the same sense exactly that we mean nuclear radiation or radioisotope radiation, although there is some overlap. I make this distinction because radiation, we have been trained in common usage to use that word to mean something that is radioactive. But in this case, radiation just means that energy is being radiated, electromagnetic energy. And indeed, visible light is a form of electromagnetic radiation. Now, there are some types of radiation that are harmful to you. You can get ultraviolet radiation that can damage your skin cells, X-ray radiation and gamma rays, and they can damage your DNA, damage your body tissues and organs. And they are categorized primarily by how energetic the radiation is. And the energy, in this case, is related to their wavelength and frequency. So as we learned before, we know that the wavelength and frequency are inversely related. And so if you have a small, short wavelength of electromagnetic radiation, then it has a large frequency. So I'll just say that again. If you have a short wavelength, small wavelength, you have a high frequency. Why is that? Because electromagnetic radiation all travels at the same speed, the speed of light. And if you have very short waves that are passing by a point in space at the same speed as very long waves that are passing by at the same speed, then more of the short waves are going to be able to pass by that point in space than the long waves. So again, the shorter the wavelength, the smaller the wavelength, the higher the frequency, the larger the frequency. And energy is higher when you have higher frequency. So shorter wavelength, smaller wavelength means higher, larger frequency, and that means you have higher energy. And you'll notice down at this end where we have shorter and shorter and shorter wavelengths, these are all in meters, 10 to the negative 11th meter, 10 to the negative 12th meter, 10 to the negative 13th meters. They're getting shorter and shorter and shorter wavelengths, which means they're becoming higher and higher and higher frequency. So they're becoming higher and higher energy as we go to the left. In contrast, on this side, you can see that the wave length is getting larger and larger and larger, 10 to the negative 2 meters, 10 to the negative 1 meters, all the way up to a meter. Larger, longer wavelengths mean lower frequencies. So radio waves are long wavelengths, and they are relatively low frequency. Yes, we talk about them in megahertz frequency, but megahertz frequency is a fairly low frequency related to the other forms of energy that we're talking about. You remember when we calculated frequencies of some visible light, and they were in the range of the times 10 to the 14th inverse seconds, times 10 to the 14th inverse seconds, compared to a megahertz, which is only times 10 to the 6th inverse seconds. So frequency is increasing as we go to shorter wavelengths, and that leads to higher energy. Well, you notice right here in the middle, I have visible light. All of the visible colors that we can see, the colors of the rainbow, that is visible light of wavelengths that fit in this narrow little band right here. And the visible light that we can see typically ranges between 400 nanometers and 700 nanometers. So we have infrared, which is below the red, and the red is around 700 nanometers. And then we have ultraviolet, which means beyond the violet, and violet is around 400 nanometers, wavelength, and ultraviolet has a shorter wavelength than 400 nanometers. Now you may see this spectrum flipped, where it has the long wavelength and low frequency on the left, and the short wavelength and the high frequency on the right. And that's okay, they're just two different ways of representing the same information. One quick follow-up, just to fill in some gaps on the next page. Our eyes can only detect a narrow range of wavelengths of electromagnetic radiation. So there's electromagnetic radiation all around us right now. It's just that our eyes can only detect a narrow range of that radiation. And the rainbow that we see of visible light includes wavelengths from about 400 nanometers, which is violet at the violet end of the rainbow, and about 700 nanometers, which is at the red end of the rainbow. In one of my laboratory experiments that I teach, we work with spectrophotometers, where you can dial in the specific number of nanometers of light and see the color of that wavelength. And one of the exercises I often have my students do is to keep dialing the spectrophotometer lower and lower and see if they can still see that color of light. And I have had several students that have reported to me that they could see into the near ultraviolet part of the spectrum, around 390 or 380 nanometers, which is just past the violet part of the visible light into the near ultraviolet part of the spectrum. Similarly, some students have reported that they can see beyond 700 nanometers into the near infrared, maybe 710, 715 nanometers of light. So that difference arises from normal genetic variation, and it has to do also with your age. As you get older, the corneas in your eyes age, and as they age, they begin to screen out some of this lower wavelength light. So I know that there were colors in the violet and near ultraviolet range that I probably could see when I was in my teens and 20s that I can no longer see now that I'm in my 50s. Just to take a moment and share a personal perspective, I think color is one of the most fascinating topics in all of science. There are many topics that are just kind of mind-blowing the more you think about them. But when you get into light and optics and really start dealing with color, how our eyes process electromagnetic radiation and then our brain interprets it as color, just a fascinating, mind-blowing area of research. Hey students, I just wanted to take a quick moment here at the end of this video to encourage you to take a look at a very short video that's online. It's called The Science of Color Perception by Calder Hansen. I think you'll find it pretty interesting. It's only about 5 minutes, but Calder goes over just how incredible color is and how our brain processes it. Have a great day.